Hello, my name is Shagoto, and now I'm gonna present my final project for CS217, which is entitled 3D Face and Object Surface Reconstruction using Calibrated and Uncalibrated Photometric Stereo. So first, let us understand the objective of the project. So photometric stereo is a method where we can get the surface normals of an object by examining it under different lighting conditions, for example, directions from different lighting directions. And for this project I have two different objectives. For part one, I have the calibrated one where I have access to the images and the directions. Then from these two I will estimate the surface normals, and from the surface normal I will estimate the depth and generate the mesh. And from the uncalibrated one I have only access to the images, so from it I'm gonna estimate the surface normals and then the depth and the mesh. So now let's talk about the dataset I have been using. So I'm using two different datasets. First one is the Yellowface dataset, which has like more than 5,000 data of 10 different objects or faces under 64 different illumination settings. And also the second one is the Diligent data, which has 10 different object images under like 96 different light conditions. So now let's talk about the methodology for part one, that is the calibrated one. So from the reflection model of the Lambertian model, we know that the I equals rho into n dot L, where I is the lighting direction, lighting intensities, rho is the albedo, n is the normal direction, and L is the different light directions. So since we have images under different lighting conditions, we can stack them, and if we denote rho n into n as x, then we can say that I equals L into x. So we have to solve this x, and we know I and L. So we can solve this x using least square method, because if n greater than equals 3, then this system becomes overestimated. So we solve this x using this equation. So then we have the albedo as the magnitude of x, and the direction of normal is basically the direction of x here. So now we have the normal. Now we have to get the depth. So to reconstruct the depth, I'm using the Franco-Cherlap algorithm. So first I'm basically extracting the gradients, which is dz by dx, which is minus nx by nz plus epsilon. Epsilon has been used here to get rid of the division by 0. So sq is dz by dy, which is minus ny divided by nz plus epsilon. Now to get the depth, we have to solve the Poisson's equation, but to solve this in spatial domain rather than, we can easily solve this in the frequency domain. So we do the Fourier transform of p as p hat and q hat, and then also the grid as fx and fy. So the equivalent equation for depth z in the Fourier domain, frequency domain, becomes z hat of fx and fy equals minus z fx of into rho hat of fx and p hat of fx and fy plus z into fy into q hat of fx and fy divided by fx square and fy square, and with z hat 0 0 at 0 to reduce or fix the ambiguity. And as soon as we get the z hat of fx and fy, then we do the reverse inverse Fourier transform to get the zx and zy. And as soon as we get the z, then we can basically get the 3D mesh using either grid-based triangulation or ball pivoting, rolling the ball. And then for the method 2, for the uncalibrated version, I have three modes. First mode is estimating the surface normal using singular value decomposition. So we know that the real world models are Lambertian, and under ideal lighting directions, they are rank 3. So we can decompose I into U3, S3, and V3. But the problem is this combination is not unique, and many combinations can generate the same I, and this is called the generalized best relief ambiguity. We will see the same in the results as well. And for the method 2, I have estimated the surface normal using a simple deep learning model, where I have the first three layers as convolutional models, like convolution input and output channels are from 96 to 64. Second one is 64 to 120. Third one is 120 to 64. And the last one is from 64 to 3 with activations such as ReLU, ReLU, ReLU. And last one is the 10H activation. So the from the last layer, I can get the normals. And for the mode 3, I have estimating the lighting directions and also the normal using a complex deep learning model, that is SDPS, which has two different stages. First one basically extracts the lighting configurations, and the second one extracts the normal estimation. So in this figure we can see that from the images they are sent to different convolutional networks to extract the local features. Then from different images the features are basically pulled together to get the global features. Then they are concatenated and sent to different layers to generate the light intensities and the direction. Then this light intensities and direction basically are conglomerated with the image and again pass through different convolutional layers mixed put together to generate the final normals. Now, if you look at the results in the top left here, we can see the meshes generated from the Yale dataset and also the color mesh. Just adding the colors in the vertices, we can see that the results are quite good in terms of the meshes for different subjects. And down here we can see the plot from the diligent data set, its ground truth normals, and with the calibrated results we can see the result is quite good. It is like quite close to the ground truth. The meshes are also good, the directions is also fine. The uncalibrated singular value decomposition is far from reality, and because of the ambiguity as we can see in the meshes as well. The surprise is from the simple deep learning model, where we can see even with shallow network we have got we have got the good normal prediction, also the direction and also the meshes are excellent. And the best performance was got from the SDPS, where we got this normal is very close to the ground truth. The meshes are also excellent. And from this upper bar plot we can see the angular errors for different models. We can see the SDPS was the best, second best was the SDL, and the third best was the calibrated, and the worst was the singular value decomposition. And for second kind of results with Buddha, we can see the ground truth calibrated did really well. Uncalibrated singular value decomposition was far from reality because of the ambiguity. A simple deep learning model again did really well, and the best was the SDPS. And also the plot with the angular errors show that the SDPS got the least and performed the best. Second was the calibrated, and uncalibrated was the third. So from my analysis, we can see that the uncalibrated versions with deep learning models can do really well, and at times even better than the calibrated ones. For example, HDPS and HDP and the singular value decomposition is far from reality because of the ambiguity. So that was my final project for CS217. So thank you so much.